You might remember in one of the previous recordings, one of the earlier recordings, I did a demonstration for you where I tore up a bunch of little bits of paper, put it on the desk, rubbed a plastic rod with the fur of an X-rabbit, and having done that, then I brought this plastic rod close to the bits of paper without touching them, and that's going to be important. And the pieces of paper responded. They jumped up in the air. They eventually, actually, some of them actually physically, what's the phrase I want? I'm sorry. The piece of paper actually stuck to. That's the phrase I wanted. The piece of paper actually stuck to the plastic rod. Okay. Just to remind you, the situation was sort of like this. That's plastic rod, and then, as I say, little bits of paper here. And I do this for you in the other lecture. And so, as I say, having brought the rod close to the pieces of paper without actually touching them, the pieces of paper experienced forces, as evidenced by the fact that they were initially motionless and then their velocity changed, and so that means an acceleration, which means a force. Okay. The question that I want to deal with is, how in the world did that happen? Well, the easy answer is, oh, hey, an electric force. We've been talking about that. The electric force calculated using Coulomb's law. That's fine as far as it goes, but how did that force actually transmit itself to the pieces of paper without the rod physically touching the pieces of paper? Apparently this force, this electric force, happened over empty space. Well, not completely empty, there was air there, but it will turn out that the air had nothing to do with it. Okay. So let's see if we can come up with an explanation. And two things. One, just to make both my drawing and my explanation somewhat clearer, I'm going to remove most of these bits of paper. I'm going to replace it with one sort of magnified view of one little bit of paper. There's that. So this drawing here, I don't want you to think that this is a great big piece of paper. This is just one little tiny scrap of paper. I've only enlarged it, magnified it, so that you can see the things that I want to tell you about. The other thing is that I'm going to answer the question and say, okay, how did the rod affect the piece of paper without actually touching it? I'm going to answer the question, or at least it's going to sound as if I'm answering it. But it will turn out that I actually am not going to answer the question, but you won't notice that, or at least you wouldn't have noticed that if I didn't warn you ahead of time. So what will happen is I will come up with my answer. I'll tell you, I'll give you my explanation, and then after that, I'll show you that, in fact, my explanation, there's no explanation at all. But it's going to sound good. So let's watch that. All right. So we now know about the existence of electric charge. I've talked to you about the fact that an object that is electrically neutral, that doesn't mean that it has no charge at all. What it means is it has lots of positive charge, but it also has lots of negative charge. And in fact, for virtually all electrically neutral objects to carry exactly the same number of positively charged objects, or the same amount of positive charge as it has negative charge, and so the two effects balance each other out, and so that's fine. However, by rubbing this plastic rod with the rabbit fur, I upset that balance. Without going into unnecessary detail, suffice to say that what happened was I managed to remove negative charges from the plastic rod and transfer them to the rabbit fur, which means that before I rubbed the rod with the rabbit fur, the rod was electrically neutral. It had equal amounts of positive and negative charge. But then, With the fur, I stole some of the rod's negative charges, leaving behind more positive charges now than negative charges. And so overall, the rod is going to have ended up with a net positive charge. Again, there are lots and lots of negative charges as well. And what I'm drawing are only the positive charges that are meant to represent only the positive charges that are in excess of the negative charges. In other words, I'm only drawing the positive charges that don't have a corresponding negative charge substance of them out. And the reason they don't is because I stole them away with the rabbit fur. So the result is then, after the rubbing event, the plastic rod has a net negative charge. That's the language we use. The thing is, though, that first of all, the piece of paper is likewise loaded with charge. Lots of positive charge, lots of negative charge. The piece of paper, being electrically neutral, has equal amounts of positive and negative charge also. So, but it does have lots of charge. Under ordinary circumstances, electrically neutral, nothing would happen to it. It wouldn't experience a net electric force at all. But when we bring this now positively charged rod close to the electrically neutral piece of paper, what happens is that the charges, that is to say the atoms, molecules, and whatnot, the particles that carry electric charge, they tend to, well, they all experience a force from these positive charges here. So there's a bunch of positive and negative charges in the piece of paper. Every one of those positive charges and every one of those negative charges in this little fragment of paper are going to experience an electric force from these positive, excess positive charges in the plastic rod. Based on the rule that I gave you earlier, the positive charges that are in the piece of paper will be repelled away from the positively charged rod. The negative charges in the piece of paper will be attracted to it. Okay? Now, it so happens, and this is going to be a conversation for another day, but without going into excessive detail right now, the paper, just as a material, is a terrible conductor of electricity. In other words, the charges that are in a piece of paper, the charges that make up a piece of paper, really can't go anywhere. They're more or less stuck in place. They just don't move. However, although they can't move from one side of the paper to the other, they can rotate. And so, to the extent that the molecular bonds that make up cellulose, in this case, paper, allow the charged atoms, charged molecules will tend to rotate, so that the positive charges, the positive side of the molecules that make up the paper are going to rotate away from these positive charges. Remember, like charges repel each other. So we're going to end up with the cellulose molecules rotating so that the positive sides of them are rotating as far away from the positive charge of the rod as they possibly can. Meanwhile, these molecules will tend to allow their the negative sides to rotate so that they're close to the, or at least closer to the positively charged rod. The result is that the piece of paper, although it is still electrically neutral overall, has one side of it that is more negatively charged, the other side more positively charged, and here comes the result. These negative charges here are closer to the rod than the positive charges in the paper are. The electric force depends on the distance. The closer the charges are to each other, the stronger the force is. So these negative charges are strongly attracted to the positive charge of the rod. These positive charges in the paper are less strongly repelled by the positively charged rod. And so overall, the net force is attractive simply because the the negative charges are closer to the positively charged rod. The result then is a small but definite force, and it tends to point towards the rod, and as a consequence, the piece of paper jumps up in the air and, in fact, even sticks to the rod if it can get that close. Okay. This phenomenon of the particles, like I said, the cellulose molecules, the atoms, molecules, whatever, this phenomenon of them rotating or separating, either rotating in space or sometimes they will literally separate, spread apart. Either way, this phenomenon that I've just described is called polarization of charge. And the overall object, in this case, is a piece of paper, is said to be polarized. So the way we say this, the shorthand version of this little discussion, is that when the positively charged rod comes close to the electrically neutral piece of paper, it polarizes the piece of paper. That causes one part of the paper to be negatively charged and physically closer to the positively charged rod. The net force then becomes attractive and the paper jumps up in the air. All right, so that's the explanation for what happened. And as I said, that sounded great, and everything I said is correct. Everything I said is true. However, it is unfortunately incomplete. As I said at the beginning of this recording, my answer here, although it sounds really good, and as I say, it's all correct, it still actually didn't answer the question. How did this force affect this little piece of paper? I still actually haven't answered that question. I will do so in the next recording.